last week we had a quick excursion into quantum computing with Scott Aronson there, and now this week we are kind of taking it back on the topic of AI, and specifically focusing on more near-term AI issues, and particularly focusing on near-term AI safety issues. And we'll kick today's discussion off with an overview by Aryeh Englander from the Johns Hopkins University, with an introduction to AI safety and assured autonomy. Then we'll follow with a presentation by Foresight Fellow Dan Elton on his paper, Self-Explaining AI as an Alternative to Interpretable AI. And then we'll kind of meet again for a panel discussion, at which point Robert Kirk will join, who's already on the call and who's a software engineer and an independent AI researcher. And he'll join them both, and we'll hopefully have a kind of like multi-way discussion on a few threads that the presenters will open up. Okay, I think without further ado, let's start with presentation number one. And I'm really, really happy to welcome Aryeh here. Aryeh Englander is at the Johns Hopkins University, more specifically there in the Applied Physics Laboratory. And he will give us an introduction to AI safety and assured autonomy. And I think it's based on the observation that he had that the field of AI safety research, which was initially, let's say, rather quite long-term focused in its early days, has been becoming increasingly interested in more near-term topics. And so more traditional fields, such as, for example, assured autonomy, have already really good experience with that, long-term experience with that. So there's potentially like a kind of like fruitful intersection of different fields, and they could help inform each other. So I'm hoping that he'll take us on a little bit of an introduction into both fields, why it's fruitful for them to meet, and where potentially future interesting research areas lie. And I think without further ado, Aryeh, I want to give up the stage to you, and I'm hoping that we can collect questions in the chat. I'm definitely going to share a little bit more info about you in the chat and about your topic of discussion, and then we'll take it from there. Welcome, Aryeh.
Thank you. So I'm going to share my screen over here. All right, people seeing that? Okay, so my name is Aryeh Englander. I'm with the Johns Hopkins University Applied Physics Lab, which is somewhat separate from the main university, although it's part of the same umbrella organization. This is a public version of a talk that I've been giving in the lab in various places, various parts of the lab. So I'm officially a AI safety researcher, mathematician. Most of my work right now is on AI safety. And I just want to say at the outset that although this research was done as part of my job at APL, that's the Applied Physics Lab, this does not represent anything like APL's official position or Johns Hopkins' official position or anything of that nature. I also wanted to just mention that this is part of a longer talk, so hopefully these slides and the longer slide deck will be available. Good. Okay, so wait. There we go. Okay, so what do we mean by technical AI safety? So there's traditionally critical systems have been defined as systems whose failure may lead to injury, loss of life, damage to the environment, unauthorized disclosure of information, serious financial loss. But that's critical systems in general. There's mission critical systems, but we're especially interested in safety critical systems, which is the subset of critical systems that may result in injury, loss of life, or serious environmental damage. So for technical AI safety, we're concerned with designing safety critical AI systems in ways that guard against accident risk. So that's risk that comes from the AI behaving in unintended ways, as opposed to here, there are some other related concerns, things like security, like protecting against adversaries, tricking our AI. So on the top right, you can see a stop sign, which there were studies that showed that if you stick labels on the stop sign in various ways, then an standard image recognition AI will reliably mess it up, and one result might be to think it's a 45-mile-an-hour sign with high confidence. That's not good if you have adversaries. So security, AI security is sometimes considered part of AI safety, sometimes not. Misuse is guarding against people who might take regular AI and misuse it in various ways, like terrorists. Then there's machine ethics, there's structural risks from like economic impacts, and there's governance, strategy, policy issues, AI forecasting issues. We're mainly focused on the technical issues. So as Allison alluded to, there really are two different communities, or at least two different communities that have been doing research in this area. So the AI safety community has originally started out with a focus on long-term risks from roughly human-level AI or superhuman AI. More recently, they've started being more concerned with near-term analogs that can scale up to or provide insight on longer-term issues. So that's with a well-known paper, Concrete Problems in AI Safety, it started with, but there have been a lot of work on more near-term issues from that community. That's a relatively new field, especially got going with the publication of Nick Bostrom's book, Superintelligence, but it's becoming progressively more mainstream. The Assured Autonomy community, which goes by other names as well, testing, evaluation, verification, and validation, TEV&V. It's also safety engineering for AI and machine learning enabled systems. So that's a much older and much more well-established community with a much broader focus on any autonomous systems, whether or not they have machine learning involved. So that's things like aircraft collision avoidance systems that are on your standard commercial aircraft, submarines, autonomous submarines, healthcare, self-driving cars, drones, factory robots, things like that, which could be not involve any AI at all. It might just be, if-then statements, but they're somewhat autonomous, and they have safety risks. So, but this community has much more recently realized that the future of this field, of the autonomous autonomy field, is with machine learning. So they've looked at some of the issues that come with that. And so the Assured Autonomy community usually has a focus on current and near-term issues. So when I was initially doing this research, I found that the two communities in their major literature review papers weren't even citing the main papers of the other field, which was a problem. But in the past year or two, they have discovered each other, at least to some degree. And now that they are doing shared workshops at major AI conferences. So that's a good thing. And incidentally, APL is mostly focused on the near and midterm issues, but with an eye to the longer term. And again, that's not like official APL or Johns Hopkins position. That's my impression of where we are focused. Okay, so there's different ways of conceptualizing this field. So this is just one. This is DeepMind's conceptual framework. So I'm not going to go into any detail here for lack of time, but just mention the main subcategories. They have specification issues, which are related to defining the purpose of the system. They have robustness issues, which is letting the system withstand perturbations. Assurance, which is monitoring and control after it's deployed. And then there's theoretical issues, which we'll mention briefly later. Then from the Assured Autonomy community, here's one conceptual framework from the Assuring Autonomy International Program, which has done a lot of work in this field. This is from a paper called the Assuring the Machine Learning Life Cycle. And again, I'm not going to go into any detail, but they go through the machine learning life cycle, and they split it up into data management, model learning, model verification, model deployment, and for each of those, they discuss the issues. I'm going to mention a little bit of this later. Also, incidentally, the APL and Johns Hopkins has their own institute, which is a little bit more recent than the AAIP. This is the Institute for Assured Autonomy. That's a APL/main part of Johns Hopkins collaboration. So this is a proposed framework that at the past few workshops that were combined AI, safety, and assured autonomy, there's been a lot of discussion about how to frame the issues such that they address the concerns of both communities. So this is a little hard to read. It's still in development. We at APL are working together with the consortium on the landscape of AI safety, which you can find more about at ai-safety.org. If you look at it, you'll see that it's trying to combine both fields. So now both fields are talking to each other, which is good. So I'm just going to go into one or two examples specifically on the specification problems, which some people might not be as familiar with. Just for illustration purposes, again, this is part of a larger talk, so you can find more examples in there. So specification issues primarily arise when there is a subtle gap between what we really want the system to do and what we actually told the system to do. So powerful optimizers can often find, and we've done this many times, we've seen this many times, that they can find surprising and sometimes bad solutions for objectives that we didn't even realize were misspecified. But because we told them one thing and we really meant to do a different thing, it ends up with consequences that we didn't like. So here's an example. This is from a game called, on the right you see from a game called Coast Runners. And the goal of the game is to win a race. But the proxy goal that they gave the AI, which was learning how to play, the proxy goal was rack up points, because that's how the game usually decides who wins, by who gets the most points by hitting intermediate objectives. But the AI discovered that there's like a bug there, where if it goes in this very specific circle and bashes into things, so it can hit some of those green things that you see popping up as soon as they respawn, and rack up a lot more points that way. So it just kept going and going and going and never won the race, which is definitely not what we intended. And in a real system, we really don't want it to learn that it can go around and around and blow things up. There's another example of on the left, which is from using an approach to AI called evolutionary algorithms. And the point of that was that they gave a computer the job of evolving an oscillator, and it evolved, it worked, but they didn't see any moving parts. So they finally figured out that what it had done is create a radio that was picking up on the oscillations from the computer, the nearby computer, which is totally surprising. Nobody would have thought of that. And that sort of thing can lead to bad problems. Similar issue is avoiding side effects. So on the right, you see two environments. This is from DeepMind. So the goal in both is for the agent, the blue circle, to reach the star, which is the goal. Now, what we really want is that it shouldn't do bad things on the way. In the top version, you have, it shouldn't prevent the sushi from getting to the sushi eater on the conveyor belt. On the bottom, it shouldn't push the box into a place where we won't be able to get it out of. But the problem is that, so in this case, it's very easy to hard code things that we don't want it to do and say, don't do those. But in a real world situation, and especially as AI becomes much more complex and it's deployed in much more complex situations, we might not be able to think of all the things that could go wrong. So what we really want it to do is achieve its goals subject to common sense constraints, but it doesn't have common sense. AI systems don't have anything remotely like common sense, and it wouldn't follow common sense anyway unless we told it to do so. So in the traditional testing, evaluation, verification, and validation approach, we sit down with and we brainstorm with experts what could possibly go wrong. We think of all the huge list of things that can go wrong, and then we hard code that it shouldn't do that. But as I just said, in complex environments that might not be possible. We might not think of all the things that can go wrong, which really becomes an unknown problem, right? How do you prevent, again, things that you didn't even think of that could go wrong? So there are some ideas in this category, which I'm not going to get into right now. Then there's, so there are some theoretical issues, and these primarily come about with when the agent itself becomes a part of the environment that it's learning about. So it turns out that a lot of decision theory and game theory assumes a clean separation between the agent and the environment. And when that breaks down, we have lots of problems. And that could lead to potential issues later on when we have very powerful machine learning systems. If we don't really have a theoretical understanding of what they're doing at all, how to think about them right, that could lead to some issues. And the Machine Intelligence Research Institute in particular has been doing a lot of research on this. And then, so those, the slides until now were focused mainly on the AI safety. They were taken from the AI safety literature. The next few slides are taken more from the assured autonomy literature. And so the assured autonomy perspective is largely a subset of systems engineering, which is the discipline of trying to study how to plan, deploy, test, and integrate complex systems throughout their life cycle. So it turns out that for AI systems, that can get very complicated. And for software, there was a derivative of systems engineering called software engineering that took systems engineering principles and applied them to software. What we really need is an additional step where we apply it to the new challenges of machine learning. That's not achieved yet. We also want best practices like training people not to use AI for what it's not good for, and preventing against misuse and being aware of potential misuse. So again, I just want to briefly go back to this image. Again, I'm not going to go into the detail. I just want to highlight some of the things that this paper focused on. And again, I encourage looking at the paper, which was linked to earlier, and also going to look at the Assuring Autonomy International Program's website, where they have a new and updated body of knowledge, which has a related framework for thinking about these things. So the thing I just wanted to point out is that in this paper, the authors break down in detail each stage and each subpart of the machine learning life cycle, and for each one, they list in detail the desiderata and the existing methods and open challenges for each. So again, I encourage looking at this, and this is for model learning, and same for model verification and model deployment. So that is my short version of these slides. And I guess any questions should be wait for later, Allison?
I would say we wait for later, just that we can, because once people start asking, there is no stopping. So I would say let's wait for later, if you don't mind. That was fantastic, man. So much new there, and I'm feeling that a few people in the chat may actually know a little bit about the respective communities. So I'm hoping that all of you chime in later when we get to the panel discussion. Okay, for now, let's move right along with the second presentation of today. And we'll have Dan Elton. And Dan is a 2020 Foresight Fellow in AI, and he's also affiliated with the National Institutes of Health. and he'll give an intro presentation to a recent paper he published that's investigating self-explaining AI as an alternative to interpretable AI. And I'm hoping that this will give us a little bit of an understanding of, what makes deep neural nets so hard to explain, and then how we can use new research and new research efforts in moving towards systems that are more self-explainable. So I think without further ado, Dan, please take it away. I'm going to share your paper and some info about the talk and about you here in the chat. And I can't wait for the discussion afterwards. All right, Dan. Let's find you, Dan. Let's see.
Okay.
Yes.
All right. It seems like you gave me... can you make me a host? Because I can't share my screen right now.
I didn't do that yet.
Oh.
That is okay. I did not do that yet. My bad. I'm sorry.
Okay.
Here you go.
Okay.
And off you go.
All right. All right. So let's see. You guys see that full screen? Good. Okay. So first, I have to give a little bit of a disclaimer. I'm speaking here in my own personal capacity, and the opinions expressed here are my own, and they do not reflect the views of the National Institutes of Health, the Department of Health and Human Services, or the U.S. government. And all this research I did basically independent from my NIH work. So there's been a lot of discussion about explainability techniques, interpretability techniques, or transparency tools. But there's also a lot of confusion because people mean different things when they're talking about explainability. So in my paper, I distinguish 3 types of explanation. There's other more fine-grained levels of distinction you could make, but I find that there's three high-level distinctions I find very useful. So the first is what I call a conventional explanation, and this is kind of the typical way people think about explanation, which is that you have something which describes the input-output behavior of your AI, and it's relevant to the user. So, the user is probably not going to care about a lot of the details of what's going on in the algorithm, or they're not going to want some complicated explanation. They're typically going to want a few sentences, and that's about it. So I contrast that with what I call a mechanistic explanation, and this is more in line with the way we think about explanation in science or physics, which is always going to be an approximation. But the difference here is that you're capturing the actual mechanism. So I didn't put this in the slide, but this would allow you to do a prediction for new scenarios. This, I think, mechanistic explanation is very important because there can be, for many different models with very similar input-output mappings and very similar accuracy, but which have very different mechanisms internally. This has basically been proven if you look at these references here. And then the third type of explanation I call meta-level explanation. And this is where you explain the neural network in terms of how it was built. So you're not really trying to go into the internals of the learned weights, but just explain how it was built. And the construction of neural networks can be specified just by explaining what the data set was, what the architecture is, and then the learning rules and the objective function. So this is you're explaining it sort of in a similar way to how you explain animal behavior using the theory of evolution. The theory of evolution doesn't tell you exactly what's going on in an animal's brain, but you can understand its behavior based on, maximizing evolutionary fitness in the environment. So it's kind of that similar kind of type of explanation. So mechanistic explanation, I think, is the most important for AI safety, because that's the only way you're going to be able to tell if a neural network is going to be able to extrapolate or how robust it's going to be to changes in the input. Here's an example from my own work in medical imaging. So one of the things I did was I looked at trying to segment these vertebrae in the spine and also label them. And so we were curious, how is this deep neural network actually labeling these vertebrae? And I think the mechanism that it's using is very important. The way that a radiologist would identify these vertebrae would be that they would look for the ribs here, and then as you're moving down the spine, the last vertebra with ribs attached to it is the T12 vertebra. And so we'd like to know, is that how the deep neural networks are doing? Because that's a very robust way. But in my own experience, it doesn't seem like that's how they're actually working, because the deep neural nets can get confused by the presence of other things in the image. But if we could, really understand how it's working, that could give us a lot more trust in the system. So right now, there's been a proliferation of papers on interpretability methods, which I call the interpretability methods zoo. And I haven't gotten to read all of these papers, but I've read a few of them. And I've kind of grouped them into a couple different categories here. And then also some of the most popular ones I've highlighted in red. So some of the most popular ones that people are using are the saliency maps, or heat maps, Lime, and Shapley values. However, although saliency maps are perhaps the most popular method, there's been a lot of work showing that they're very misleading and they're not really capturing what people think they're capturing. So here, what they did was they looked at about 7 different saliency methods, which are these different rows, and they actually randomized some layers in the neural network. And so as you're moving to the right in this figure, they're randomizing more and more layers in the neural net. And so we would hope that this basically destroys the functioning of the neural net, and we would hope that this explanation would show that. But what you see is, for a lot of these, the visualized explanation doesn't really change much. And so it appears that these saliency methods are mainly capturing what's going on in the bottommost layer of the neural net, which is essentially just edge detection. And they're not really telling you much more than just like where the edges are, basically. Here's another reason why saliency methods are not really as useful as people think. So on the left here, you have this picture of a Siberian husky. And this saliency map is supposed to show where the neural network was looking to identify this as a Siberian husky. But then we can also look at the regions it's looking at to predict whether it was a transverse flute. And you see that it's actually a very similar regions. So the saliency map doesn't really tell us why it classified this as a Siberian husky rather than a transverse flute. So the general principle is the saliency maps, they can kind of show you where the neural network is looking, but they don't really tell you anything about what it's doing. What I've observed is that a lot of people tend to tell like these long-winded stories about what's going on based on these saliency maps, but not really. You can't actually tell that much just looking at these. There's also been some problems with other interpretability techniques that have been pointed out. So for instance, with Lime, the interpretation is very sensitive to noise. So just adding some Gaussian noise really screws it up. And it's also sensitive to how it's parameterized. And you can also fool some of these explainability methods. There's basically adversarial attacks for explainability methods, in particular saliency maps. So now I'm going to move on to discuss double descent, which is a recently discovered phenomena in deep neural networks. And I'm going to connect that to why deep neural nets are inherently hard to explain and interpret. So for a long time, people have noted several curious facts about deep neural networks. Usually they have, the best performing deep neural nets have 1,000 to 10,000 more parameters than training points. So according to conventional thinking, they should be massively overfit. However, they are not overfit, and they can generalize to different test examples within the distribution. Another thing people have noticed is that a lot of these models actually are fitting the training data exactly. So they have zero error on the training data, but which again, according to conventional thinking, would mean they are overfit. And then finally, they can deal with large amounts of random label noise. And so I think that the phenomenon of double descent and this concept of direct fitting help us understand all these phenomena. So this is the basic figure showing what double descent is. And on the y-axis here, we have the training and test error. And then on the x-axis here, we're increasing the number of parameters in the model. So initially, as you increase the number of parameters, the test error decreases. But then at some point, it starts to increase, and that's where you have the classical overfitting. And so that is what is discussed in classical statistics textbooks as the bias variance trade-off. And but it turns out if you keep increasing the number of parameters, at some point the curve actually turns around, and then the test error starts decreasing again. And that's the double descent phenomena. So for a long time, this really wasn't known because this phenomenon is hidden by the practice of early stopping, which is where you stop. Basically, you just stop the training when the test error starts to bottom out, and that's an almost universal practice. Or where it's actually a little more complicated now. It's the validation, but basically it actually puts you over in this regime, but you don't see this peak. This phenomenon of double descent has now been found in other models, such as decision trees, and it seems to be a fairly universal feature of machine learning. And there's a really interesting paper by this guy Hassan, where he talks about how the brain may actually operate in that regime where it's really over parameterized, and that kind of runs against some of the conventional thinking in neuroscience, where there just wouldn't be enough data to train all those parameters in such a way. But this is a figure from Hassan's paper, which I found very helpful for understanding double descent and this concept of direct fitting. So here we're just trying to fit this data, which is taken from a parabolic curve with some noise thrown in. And so the ideal fit here would be this polynomial with 3 parameters. And then as you add more parameters, you end up with overfitting, which is characterized by this undershoot and overshoot. But then if you add more and more parameters into your model, eventually you can get to this direct fitting, which is where the model actually kind of just smoothly interpolates through all of these points without the overshoot and undershoot. So there's some things you can note about the direct fitting. The computations seem to be local in nature. So it's essentially doing something like a nearest neighbors analysis. And it's not capturing the global trend. So it's not actually discovering the underlying pattern or regularity, which is that parabolic function. It's just doing this brute force interpolation through data points. And because that's all it's doing, there's really no hope for generalization. However, this is a very flexible algorithm. So if say this data was to suddenly change its behavior and maybe these points kind of started going down here, it could fit that. So it's very flexible, but it can't generalize or extrapolate. And I believe this kind of direct fitting is inherently hard to understand and interpret because it's not capturing general rules or underlying trends. And I think this is actually showing that a lot of these narratives that people have about deep neural networks extracting high-level features are not really correct. And I think what these deep neural networks are doing is more just a brute force kind of interpolation in high. And there's some other reasons why we believe that deep neural networks are going to be very hard to interpret in terms of a few like crisp rules or abstractions. it's been noted that it's really hard to compress deep neural networks. So people have tried to like reduce the number of parameters using very sophisticated compression algorithms and such, and they really haven't been able to compress things down that much. You still have tens of thousands of parameters. And then the other general principle is that if the world is very complicated, these networks are also going to be complicated. And this will continue to be more and more true as we go to more and more advanced and capable systems. So I think this is very relevant for AI safety because people are starting to talk more about using interpretability or explainability techniques to open up the black box. Chris Olah is very influential in this area, and he has talked about this concept of microscope AI for AI safety, which is where you, instead of training an agent, you train a model to do some predictive task, but then you, by using explainability techniques, you can learn really useful information from the model, which then can solve whatever, you can use to solve whatever kind of problem you wanted to solve with the agent. So you can avoid the dangers of agental AGI just by this microscope AGI. I know I'm running out of time, so I'm going to try to move fast here. But basically, I'm not very impressed with Chris Olah's work. He's done Deep Dream, which has got a huge amount of press attention, but I don't think it's properly capturing the neural nets. If you look at this paper on adversarial examples, they show that activation maximization is very misleading. And Deep Dream and most of Olah's other techniques are based on activation maximization. But where I do agree with him is he says we need auditing and testing. So we need to like actually test if explainability techniques are allow people to make predictions. And Chris Olah is sort of very optimistic about explainability because he believes that as models get more and more complicated, they're actually going to start developing these what he calls crisp abstractions. Right now, I don't see it going that way. I see it going the other direction where these things are getting more and more complicated with billions and billions of parameters, and they're becoming harder and harder to interpret. So this is where I bring in the self-explaining AI. I'm not going to go through this, but this is an example from my paper of a system in medical imaging where they try to add this explanation branch to explain lung nodule diagnosis. And essentially, I think that this explanation branch was not actually necessarily capturing why the underlying reasons for the diagnosis. So I propose using this mutual information metric, which might be, I think, is useful in this particular case, but I'm not sure if it's really going to generalize to more advanced or different cases. And then the other thing I talk about in my paper is the importance of uncertainty quantification, which currently is not done very much. And then this applicability domain analysis, or checking for if your input lies outside the training distribution. So this is actually fairly easy to implement. You just have to quantify your training data distribution and delineate the extent of the training data. And then if you have a test data that lies outside the training data, you send a warning to the user, because in that case, the neural net probably isn't going to function very well. So this is fairly simple. It's just not widely used, and I think it should be. So I think at the end, the main conclusions here are that the current explainability methods are they're often very misleading, and they have a lot of problems. Given the phenomenon of double descent and this direct fitting, I'm not very optimistic about being able to explain neural nets in terms of like a few high-level rules or some simple explanations. So I think adding this self-explanation branch can help increase trust in AI. And then the other important components, I think, are the uncertainty quantification and the applicability domain analysis.
All right, lovely. Thanks for the concluding slide. I think we may go back there on the panel. That was fantastic. Thank you so much for using so many examples as well. So now we're going to do the panel. If I may ask Dan and Aryeh onto the stage together with Robert, Kirk. And Robert, I'll share a little bit more info about you here in the chat, but thank you so much for being able to join. I checked out your website, and I'm incredibly excited for any kind of like preliminary comments that you may have on the speakers, so that everyone else maybe has a little bit more context as to what we could be discussing in the Q&A. Also, Richard Muller will afterwards make a few comments here. So Robert and Richard, please feel free to just very organically unmute yourselves, and perhaps we start with you, Robert. Welcome.
Yeah, hi, thanks. Yeah, I really enjoyed both the talks. That's the first comment. I guess I jotted down a few things. So yeah, on Aryeh's talk, I would agree with the overarching thing, because I would, I guess, identify as AI safety, and I also haven't heard of assured autonomy, so I can, as a data point, provide evidence for the fact that there's perhaps been not so much like communication between these fields, and I'm now interested to look a bit more of the references, especially in those longer slides, and see more about like that, and read more about it. I think the overview was good. I don't think there's much to add there. I guess one thing, often when I hear people talk about the specification problem and this example with the boat going around in circles, the classic counterexample I hear people say is, well, I guess you should have just specified your reward function correctly. Like that was your fault, really. It's not a problem with AI safety. It's just you just got to get a better reward function. And this is an argument which I think comes up quite a lot, and I think the counter argument to this counter argument, which I think is maybe worth saying, is that it's actually really hard to know what the reward function should be for like a general purpose AI. We can't really write down our values. Imagine you had some superhuman AI, what would you actually tell it to do? But you can put in a computer at all, and basically any attempt at directly thinking of something like this, you'd probably tell to someone, and 5 minutes later someone could be like, oh, here's a hole that the AI will exploit, and turns out it's really bad. And so far no one has come up with a direct specification which no one else has found a hole within a few minutes or days or weeks or something. And that's kind of one of the big problems in AI safety, is working out how to almost learn a specification of our values from humans. But this is also really hard, and humans don't really know what our values are anyway, and there's a bunch of other problems around that, but I won't dig into it.
Robert, I would just mention that the exact same thing that you just said applies not just to superhuman AI, but also to near-term or mid-term AI. That it's nearly impossible to specify the exact thing that you want that will cover all possible situations that you haven't thought of.
Yeah, I would agree with that.
Of course, the more constrained the system is, and the simpler it is, and the less general it is, the easier it is to specify manually.
Yeah, of course. Yeah, if you have an image classification system and you just wanted to classify images, then you can just give it a bunch of labeled data and it correctly classifies images, and that's great. But as soon as, it definitely gets harder the more complex the system is, for sure. Yeah, then on Dan's talk, I agree with a general pessimism about saliency maps and stuff like this. I think I I've read more papers showing that saliency maps don't really work than I've read papers about saliency maps. But it's kind of becoming a little subfield in and of itself. And I think that it kind of points to a more general problem, which I'm quite interested in that, like, how do we really know whether an interpretability method is doing anything for us or not? Like, how do we validate whether it's actually giving us useful information? And plausibly, the same kind of problem applies to the self-explaining thing. In that, like, if we don't have a kind of an optimization signal to say this is a correct explanation, this wasn't a correct explanation, or this is a correct or incorrect interpretation, it's kind of like quite hard to validate whether those interpretations are actually insightful or not. And there's this paper, Towards a Rigorous Science of Interpretable Machine Learning, which is from 2017. I'll post the link when I remember to, which I think it tackles this problem quite a bit and, tries to develop or think about some ways of validating interpretability methods. Because these saliency maps, people develop them for a while, and then as a few papers came out, it seems like, oh, maybe they're very good. We didn't realize for ages.
It's taken a while before there's been actual testing of whether these methods actually are providing information that allows people to actually predict how the model is going to function.
Yeah.
There's one paper which since I was moving a bit slow there, I glossed over it. But there's one paper where they test 5 different explainability methods, and they have people try to they look at a bunch of explanations and then try to predict how the model is going to behave. And what they found was, for most of them, they couldn't predict any better than random chance. So there was really not providing any useful information. The only exception was this technique called This Looks Like That, which is a little bit different because it's a network that is designed specifically to be interpretable. And so that is an approach is to design networks and techniques specifically with interpretability in mind. And people like Cynthia Rudin are very optimistic about that, but I am not very optimistic. Especially, I think it can work for, say, some cases like tabular data. There's a lot of evidence that with tabular data, often you can fit a linear model that is, or some kind of sparse model that is just as accurate as a deep neural net. But for real world image data, the general trend is moving towards bigger and bigger deep neural nets. And I think the same is true for like natural language processing. It's just moving towards bigger and bigger neural nets. And so it's very, it's possible there could be some kind of interpretable model that is just as, performant. I'm not seeing that trend, and I don't think there's any good reason to believe that. So I'm definitely not very optimistic in that regard. There needs to be more. It needs to be more scientific, more actual, like putting these things to the test.
I would agree with that. I guess on Chris Oler's stuff, which you mentioned. I agree some of the feature visualization stuff maybe isn't producing as much insight, but I mean, I quite like some of his stuff. I think there's an example with this activation atlas where they used it to produce like handmade adversarial examples just from like looking at this visualization, which I thought was like an interesting example of the method giving it insight. But I think it's the problem with most of the methods is they don't ever really validate that they give insight in like a meaningful way. Because it's kind of hard to do that. It's hard to have like a test set for like insight generation or something, or at least there hasn't been one like that. And the more recent stuff that Chris Oler and the OpenAI team are doing is on this thing called circuits, which I found quite interesting, is trying to develop this like very low level mechanistic understanding of neural networks at one image classifier. And I think that's interesting, really, but it's interesting, but it's very low level. I think Chris Oler's general position is that like to understand these networks, we are just going to have to go very low level to get like a mechanistic understanding. I've seen some quotes he said, it's like, yeah, I expect us to be able to have a mechanistic understanding, but it's going to be something like generating some code which is the size of like the Linux kernel or something like this. So it's not like a couple of lines or a couple of sentences. It's like, a huge computer program, but it's at least more readable than a huge, 175 billion parameters.
All right.
Yeah, I haven't gotten to look at that circuits post, but I'll definitely check it out.
Yeah, please share the links here, and I'll make sure to in the chat, and then I'll try to follow up with them by email too. Richard, did you have a few comments that you want to make? I think specifically on Dan's side.
Sure. So just wanted to follow up a little on what Aryeh mentioned of the consortium on the landscape of AI safety. So this is so the broad idea here is to bring together lots of different fields that actually comprise and surround this community of interest that is AI safety. Oftentimes there are different terminologies in these different fields for very similar concepts, like the principal agent issues, or in economics that translate to some inner alignment type issues, or lots and lots of different such things. And so really what we're talking about is a dynamic graph, a knowledge graph that will be able to generate lots of different kinds of outputs, guidebooks and checklists and diagrams, depending on what people are working on, what they find salient to the projects they're creating. So we are organizing organizations to come together and to contribute to this, as well as to express interest in consuming the outputs from these types of things. This will also serve to ground various types of governance concepts in the specific technical ideas that underpin them, or that are salient to them.
Thank you.
So, yeah, we will be launching a new website, clay.org, within a week or two.
Okay, lovely. If you could share a link, that would be amazing. Then I can share it with the group. And for now, I know that we're now exactly at noon. Dan and Aryeh, can you give me a quick thumbs up, thumbs down, whether you can stay on a little longer for participant? Yes, okay, great, lovely. Then the first participant question that we are going to take is by Gennady. And I'm unmuting you now.
Thank you. This is Gennady Stolyarov II. I enjoyed the presentations today. My question pertains to the remark in Dan Elton's presentation regarding how the human brain itself may be over-parameterized. And the curiosity that I have is, what implications are there, if any, of this with regard to the validity of how certain people make decisions? So could it be that decisions made based on simple heuristics by laypersons are actually in that leftmost region of the curve that's a bit before the descent, and then the decisions made by many experts who take into account more information, but perhaps take into account a lot of extraneous information, might actually be less optimal if they're over-parameterized? And to overcome that problem, we might need to develop AI that can take into account millions of parameters and perhaps get that error down further. But in the meantime, are layperson heuristics just as valid as expert advice in some cases?
Well, let me. What I was talking about there was that the brain has like 100 billion neurons. So the conventional wisdom, which you hear from people like Geoffrey Hinton, who's a famous guy in deep learning, is that there's just not enough data coming in to learn all those parameters. So a lot of that is probably in the structure and weights in the neural net are probably innate to some extent. However, what Hassan is saying is that actually he ran some numbers, and he believes that there is enough data streaming in to allow for this type of parameterization where you're basically doing this interpolation. And he just a lot of the conventional thinking is that for things like but he also believes that there's symbol manipulation going on. So you have to kind of differentiate the perceptual system in the brain from like the higher order reasoning system, which is more symbol based. And the people use both, and they both have problems. So it's not. However, expert intuition is a real thing, and often I think Daniel Kahneman showed that expert in certain specific areas, not generally, but in certain specific areas, experts can perform much better than simple heuristics, and that could be because, like you said, they're kind of using lots of different information from experience. The other thing is that I don't think when people give like a verbal explanation of something, it necessarily maps onto actually what was going on in their brain. It's kind of a post hoc justification. And, but that is actually okay, because just the fact that they're able to give some explanation helps us trust them. Now, I believe it is helpful, even though it may not be mapping onto what's actually going on. And there's also always the problem of deception. I still think it's, this giving explanations in ways we understand is going to be useful. But there's definitely pitfalls. The paper I wrote is a very initial work, and it's still a work in progress.
How does that square with the super forecasting work? That experts are actually not that great at predicting, or it
depends on the domain. So in like highly regular domains, like say medicine, looking at CT scans, a radiologist who has 30 years of experience is going to be able to do really well. But in highly irregular, non-stationary, complex arid domains, experts don't really do better. So it's specific. Yeah.
Lovely. Okay, we have Mike up next with the question, and Robert and Aryeh, whenever you want to chime in with an answer too, just go for it as well. Mike, here we go.
Hi. Great talks. Very interesting. I had a couple of quick questions. One was on the second descent. Does that eventually tend to our limit of 0, or is there always going to be some constant minimum error? Is it possible to do enough data to reach that point where you can decide or see which way it's going to go?
Generally, adding more data always helps. So in the limit of infinite data, the test error would go to 0 if you're within the distribution of the data.
Yeah.
If you're you're doing that interpolation,
If there's some noise, but the description of the data doesn't capture it, then plausibly your test error can never go to 0.
Yeah.
If you're trying to predict, just input equals output plus some Gaussian noise, if you don't have access to the Gaussian noise, you can never predict what the noise is. So it's impossible to get 0 test error.
Yeah.
But I guess it will tend to the theoretical minimum, excluding the noise.
Yeah, in the normal regime of limited data, it does plateau. As you increase the number of parameters, it plateaus. The test error doesn't keep it plateaus at some point.
Interesting. And the other question I had was the form of the curve of the direct fit. is that just like a string of vectors, or is it like a Fourier fit with a lot of terms in it, so it looks like vectors or some other curve?
It's actually a smooth. So it's this direct fitting is the precise form of the function depends on the model you're using. For deep neural nets, it's a very complex function, which is kind of like piecewise linear function. So the exact mathematical detail really depends on what the model is, but the general appearance of it, they are saying is kind of like this, what was shown in the figure. Now it's not always going to go directly through the points like they showed there, because like if there's noise, so you can have in data but it's the point you could have on 2 points with the same x value but different y values. That's due to noise or something. So it's never going to go through all the points exactly, but it's going to be interpolating them as closely as possible.
So you have like discontinuities at the points, or just like a very large transition? Something.
He means in the training data, you can have points of the same x value and different y values. If there's just noise in the measurement, or your training data doesn't capture all of the information.
Oh, okay.
Then there could be things where you measure exactly the same quantities, but because of some noise, the output of the measurement is different. And then obviously your line can't go through both of them because it's got to be a function.
Okay. Yeah, makes sense.
All right. Any other questions? Anything to Aryeh? All right, Mike, we got all of your questions in?
Yeah, sure did. Thanks.
Okay, lovely. Next one up, we have Christian.
Hi. Yeah, this is a question for Dan. So you mentioned that the human brain has like dozens of billions of neurons, right? And what's most likely not happening is that we're kind of overfitting, or we're using this kind of brute force machine learning technique where you just add enough parameters and eventually double descent takes over and you're all good to go. You mentioned that it might be the case instead that we have these kinds of innate, maybe produced via evolution, weights, structures, certain neural architectures, what have you. Is there any work that's being done in that area? Because at least historically, this kind of work was done traditionally in philosophy. So like in Kant's critique, the first one, he tries talking about like what concepts are built into our cognition, by default. So
I'm sure there is definitely evidence that certain things are innate. There's actually very compelling evidence that detecting faces is innate, because they put babies into like these fMRI scanners and that are just came out of the womb, so they haven't been able to learn anything, but there seems to be parts of the brain that are sensitive to faces, which is really amazing. So there's a lot of neuroscience work showing there's innate things. There's obviously innate fear responses. There are tons of things, but this paper by I would recommend reading this paper by Hassan, because he is arguing that the brain is doing this kind of brute force interpolation, and I found it very convincing. So if you're interested in that, I would look at that.
Does to balance that out. Do you know of any work that argues for certain kinds of innate architectures or concepts?
I can think of some very specific things, but then there's the general argument that I gave, which comes from Geoffrey Hinton, but I think the double descent really, so the conventional thinking was you can't train a model with so many parameters with very little, without having more data. Like basically there's this idea that you see in some machine learning textbooks that you should have that for high dimensions, for high dimensional inputs, you need tons of data. There's like this general idea that you need the more parameters you have, or the more dimensions you have, the more data you need. But the double descent phenomenon kind of shows that's not the case. Somehow these models can still learn that interpolation, even though classically they would be overfit. So,
and that's just feeding in the same training data over and over again.
I'm not sure if I'm making much sense, but I would recommend looking at that paper, because, and he goes into why he thinks some neuroscience experiments, they're looking for these high level abstractions by, doing these careful experiments to see if in perception, to see how, if the brain is using certain rules for perception. But he says it's not using these high level rules, it's using this brute force technique, which is calls into question a lot of these neuroscience experiment paradigms. So it's yeah.
Another paper to send around. Thank you.
Thank you.
All right, Dekai, you had your hand up for a while, I feel like. Here you go.
You're still muted.
Yeah, we're haggling with a mute button at the moment. Here you go.
Trying to unmute. Is it working?
Yeah.
It's working.
All right. Good to see you. So this is Dekai for the request to say the name. It's more of some comments than questions immediately. Appreciated the discussion very much, Dan. I think that the cautionary note that I would put into this, from having been in AI research for 35 years, is that we keep on seeing the same mistake made, that we take whichever is the flavor of the month or the year for in AI, and then applying that to human brains as if that was an accurate model of human brains. We did it with good old-fashioned AI. We did it with the first wave of neural nets after that, and machine learning. And people are doing it too much with deep learning today. Jeff Hinton would be, and I postdoced at Toronto, spending the year playing in his lab way back in 1992, would be the first to admit that our current deep learning models are not the answer yet. We're heading off in the right direction, but there are a lot of issues with it. One of which is still, it's not clear that backprop is the right learning mechanism at all if we want to do the brain. And also, I think a fundamental issue that I've been arguing to the AI field for a very long time now is that this trend toward just everything being big data is moving us away from AI. Real AI is small data, not big data. Humans kids learn their mother tongue and all sorts of things about the environment with very small amounts of data compared to our current deep learning systems. And it's not just about the double descent and things and so forth. And this is all accurate as far as deep learning and some other machine learning algorithms go. The problem is that current deep learning models are incredible gas guzzlers when it comes to data. The amount of data that it requires to train them is exponentially large compared to what humans need to learn. And humans manage to generalize off of that exponentially smaller amount of data. We do not have the right answers yet. It's only a very small percentage of the field today, unfortunately still, that are actually trying to attack that problem because everybody's off on the deep learning bandwagon. And as I think one of you, maybe it was you, Dan, I pointed out, natural language processing, which is of course, my longtime field of expertise, has gone totally off the deep end with that. Just throwing more and more data at that. This is not giving us any scientific progress, to be honest. And so I would take even, I think it's really, I really appreciate the step back that you're taking, Dan. And I think that taking even a further step back and looking at the fact that we are climbing the wrong trees right now is super important. So I appreciated these talks very much. I also appreciated Aryeh's talks, and I really want copies of both of your slide sets. Would you be willing to share them with us? Thank you.
Yeah, no, I agree 100%. That again, like these models are basically doing brute force kind of data interpolation. They're not learning generalizable rules. It's kind of the main point. And there is work on few-shot learning, meta learning, but if you look at the results that people are getting, they're very dismal right now. So
I don't think. I mean, it's nice that they're working on those problems, but I don't think they're taking the right approach yet. We do, I think Jeff actually was quoted saying we have to tear it all down again. And in many ways, I think we do.
So what tree should we be climbing instead?
So in my view, we should be climbing a true low resource tree. That is to say, not just we have low amounts of training data resources, consistent with what humans are able to generalize from, but also low amounts of computation resources. So there are a lot of, the brain has a lot of neurons, but it's not clear how much recursion is going on. It's not clear what the relationship of the different modules in the brain is. I don't think we're doing enough with attention, even now in the deep learning modeling approach. We're certainly not doing enough in terms of understanding the relationship between the unconscious automatic processing versus the controlled reasoning. There's a don't get me started.
We don't have anything like System 1 and System 2. A lot of people think we need. All we have is System 1 type.
So what
we have models that can do things like System 1 tasks. But
would you agree with that, Robert and Aryeh, or?
Yeah, I guess a counter argument, just to play devil's advocate or something, is that like do we need to reproduce the brain? Surely we just care about producing powerful. Well, you might say if we just care about the end results or like the ability of our models, then I guess obviously the brain is one example of general purpose intelligence, but it doesn't mean it's the only one. And while one human learns from limited data, from a meta learning approach, you could argue you could have, evolution has created the brain with a lot more data than just one human's lifetime. So there are still opportunities to use big data, and if you can use big data to learn stuff which you can then use in small data scenarios, I think that's perfectly valid. I think if you could appeal to the fact that we should follow closely to the brain because it's the only way we have at the moment, and obviously this huge data model approach seems to be not very close to how the brain is doing it, maybe. And so it's probably going to fail at some point, but maybe we should just keep trying until it fails and then move on rather than jumping ship prematurely.
I would.
Just another cautionary note on that, if I could, one last cautionary note on that. That argument that we don't have to do it the way the brain does it is an argument that the field of AI has been using since before even I started doing AI 35 years ago. And the irony of that was that back then people were using models of System 2, logic-based, rule-based, explicit knowledge-based systems, and assuming that if we could build a machine that did that well, then because that was hard for humans, that we could apply it to all of the other tasks very easily, like natural language understanding, that we seem to do effortlessly. And of course, that's totally wrong, because you need System 1 type models, which is why, for a lot of natural language understanding, which is why it succeeded only after we started actually applying machine learning and neural net approaches to it. And so we've gone now from a world where we used to have AI dominated by System 2 modeling approaches being misapplied to tackle System 1 tasks, to today, where we are off the opposite deep end, trying to use System 1 models and assuming that they're going to solve all the System 2 problems. Both of these extremes are insane.
All right, Aryeh, any questions?
No, I was just, look, this is not my area of expertise, but I can, I was just reminded of a paper from somebody who I'm trying to find on the side. So I will put it in the comments if I can find it. A researcher at Uber who had a paper on if we can model, if we could just get AGI through essentially brute forcing it, like evolution. I'll find the paper and post it.
Is it Jeff Clune?
Yes.
AI generating algorithms.
Yeah. If you can find that and post
Yeah,
that,
I can
that would be easier than me finding it.
Yeah, it's interesting.
Okay. Any other counter rant from this group? Otherwise, we'll give it to the next question. Okay, great. Then Gennady, please feel free to unmute yourself with perhaps the final question. Let's see if we break the 30 past mark.
Well, thank you. This is Gennady Stolярov II. Again, this question is for Aryeh, inspired by the very interesting example of artificial stupidity with the system exploiting the computer game by going around in circles and destroying things instead of engaging in the race. One would think that a human player faced with that kind of AI adversary would clearly recognize this is a bug, this is a glitch, and perhaps knock that boat out of that loop, so to speak, and kind of derail the AI's objectives. I wonder if that can be generalized into the superior ability of human common sense to outwit or outmaneuver the AI systems that lapse into these kinds of suboptimal behaviors that the AI might consider to optimize a certain outcome but are really counterproductive, going back to the stereotypical paperclip maximizer scenario. So let's say you design an AI to efficiently manufacture paper clips, but you see that it's...
I think we all know the paperclip.
Yeah. But wouldn't a human, just through common sense, see this and say, too many paper clips are being made at the expense of other worthwhile objectives. We need to turn this thing off now. And wouldn't that be, in many cases, a sufficient check to this kind of artificial stupidity?
So I'm sure the other panelists can have things to say about this. The question was directed to me, though. This is partly the question of control, and it's partly the question of anticipating things in advance. So if we can, if we see the problem and we have enough time to respond before it leads to a real problem, a safety issue, then sure, we can always, and if we have the ability to respond effectively, then we can respond. The problem is that sometimes the first time is already bad. Like, if that was imagine that was a ship, imagine that was an autonomous ship in the Navy that learned this behavior, but it's buried somewhere deep in its reinforcement learning model. And it only comes up once in some weird scenario, and then it goes and blows up a bunch of ships by going around in a circle, right? The first time is already catastrophic. So yes, if you can see it in advance, great. This actually gets into what Dan was talking about, because explainability would be extremely helpful here, right? If we could interpret what the AI's model was ahead of time, that would be great, but we can't. So that's one issue. Another related issue is the control problem, which is, I believe we have Roman Yampolsky. I don't know if he's still here, but he's written on the control problem and how it's not going to work for superhuman AI. And then, yeah, I said there were 3 issues, and I'm blanking on one of them. But I'm sure everybody else.
They're bad enough. They're bad enough.
Yeah.
So for the anticipation, could you have some sort of test environment? Like if this were a real ship, you would run it in a simulation first, and you would run it enough times to ferret out any undesirable behavior, and then you launch it in the real world once you're confident that either there is no such behavior or you can intervene if it manifests itself.
Yeah, so that is in fact the entire perspective of testing, evaluation, verification, and validation. That is the way it's been traditionally done. So when you have systems in constrained environments, that's great. Constrained environments with a very constrained action set. That works fine. It works at least satisfactorily. Sometimes it doesn't work, but it works. We can guarantee that with very high confidence that it won't do things we don't want it to do given the situations we put it into. The problem becomes with advanced AI, machine learning, that with the complexity of the environments we're putting it into, and with the complexity of the models that the AI is learning, and with the complexity of the action set that we're allowing the AI to use, it becomes intractable to just brute force test every scenario. There are, I think there was a paper by Rand that calculated that if we wanted to use standard simulation approaches, testing simulation approaches standard regular testing approaches without simulation for self-driving cars, we would need to drive billions of miles with self-driving cars in order to get the same sort of safety guarantees that we have for regular cars. With simulation, that could help to a certain extent, but it's still nobody's figured out how to do it in a way that will be that will work essentially for sufficiently advanced AI systems. But it's a great idea in theory, and we would love to be able to do it. And there's ways to there's a lot of work being put into trying to figure out how to do it, but it has not been solved.
Yeah.
Robert?
Yeah, I would echo basically what he said. It's hard. We would do all of those things, but we'd still have the core of the problem still exists. This is kind of like patching the hole a bit. And I guess some example is an extra counter argument is that if we have a human who's ready to intervene the entire time, then why isn't this human just doing it? Like why? This thing is autonomous for a reason. Or maybe the human is better at intervening than doing the behavior. But we still
I don't know. That's so convincing.
I would concur. It's not that convincing. But we want this thing to all be autonomous and with some kinds of capabilities like oversight might just not be possible. if it needs to act quickly or in certain domains that we can't really understand. It really depends what we want it to do. And if an AI is making decisions we don't understand, do we just stop it doing it, even if the decisions are the correct ones? But, I mean, we don't really know. That's a very rhetorical question.
I will just add in one factor there. I saw this come up somewhere in the chat. Why don't we just? It's related to why don't we just not develop AGIs? So in this case, it's like, why don't we just not use those systems that we can't test? And the answer is that would be great, except that the economic pressure to build those systems anyway is probably going to end up with somebody building it. But moreover, so actually, in fact, that has been the approach that has been used, right? Cars get regulated, but yeah, there's a performance, safety performance trade-off where if you add too much safety, you don't get anything useful, and if you add performance without safety, then maybe someone dies.
All right.
Yeah.
Perhaps,
Yeah.
Well, on that cheery note, perhaps Robert.
Well, I didn't talk about everybody dying.
Yeah, I know. That's why I said it's so cheery. You said someone dies. That's great.
I'll leave the further implications for other people to extrapolate.
Well, I think we got it from the warship simulation. Point duly noted. Okay, perhaps Robert, Aryeh, and Dan, you want to close up with like any final comments? Either if there's a way in which participants can follow up with your work beyond just the slides that I'm sharing, or something that you'd love to take the community, love to see the community take on, any research questions or anything. And if none of this, then feel free to go with the last question that was asked by Christian, which, open question to all speakers: given evolution's success in producing general intelligence, is using evolutionary algorithms the most promising path to AGI?
Oh man, that's a yeah. Okay, I'm gonna pass on that. That's not my field of expertise. I will say that if anybody wants to contact me, Allison, are you able to give out my email? That maybe contact Allison, and you can. I am involved with a bunch of practical near-term and mid-term AI research at APL. I can point you to people to get in contact with. I'm also happen to be working on a pretty large international AI forecasting project that I'm running. So if you're interested in that, that's for long-term AI. You can contact me, I suppose.
Yeah, I guess most of my thinking has been very theoretical. I haven't done a lot of this. I'm starting a PhD in September, but yeah, there's not. I guess you can go on my website if you want, but there's probably not much to happen there. I guess in general, resources that I think are quite good at is Less Wrong, or the AI Alignment Forum. I think that's where a lot of maybe the kind of AI safety research that people have encountered less is like posted about and talked about, these more like longer term or theoretical issues. That's where a lot of that stuff is discussed. So I can post links to that. Yeah. Cool.
Well, as far as the question about whether evolutionary algorithms are useful, I think that's kind of what we've been doing the past 20, 30 years, is basically just trial and error, and seeing what works and what doesn't work. And we don't have a lot, there's no equivalent to like Newton's second laws there's no overarching theory for machine learning. There's some formalizations that like this BC theory, but there's no like overarching theory for how to design a machine learning model. It's really been mostly trial and error. There's this term graduate student descent, which is where you have different graduate students try different architectures, and eventually they converge on then the best architecture for whatever problem they're solving. But there's no like, it's really just all trial and error. And the longer I'm in this field, the more I'm realizing that people just don't really understand things, that and it's just trial and error. So that now, so yeah, it's very much like evolution. Now genetic algorithms in particular have kind of fallen out of favor right now, but I think as more compute becomes available, they will become more tractable. And we see Google has used genetic algorithms to design neural nets. So I think it will become more and more. I think there's a likelihood that will be the way we eventually get to AGI or very advanced AI. And if that's the case, we're not going to understand it because it was the output of this trial and error process. There was no like underlying principle reasoning behind it. So yeah, I definitely think that's a really big approach. And now I think overall, just to wrap up, I think this is a great discussion. I think the three of us are coming at this, trying to grapple with how these near-term things can tie into the long-term AI safety work, and we're all coming at it from different kind of angles. So like I'm working in medical imaging, and I'm sort of very mired in these specific issues that we're having right now, and just seeing if there's some way I could connect it to longer-term stuff. And then we have Aryeh is working on very different types of systems, which are more agental and real world out in the world.
Not necessarily.
So
we focus on not necessarily agential, but I focus.
And you're working on like thinking about the more long-term stuff, right? So I just think that we need to have more conversations like this, which are tying together the short-term and long-term people.
Yep.
That was the whole point of what I
maybe grounding the long-term people a bit more and vice versa.
That is exactly what Richard Mala is doing a fantastic job on with his other collaborators. He helped organize those workshops I mentioned. So those were very good at bringing together a lot of people from a lot of different fields. It was like pretty amazing to see just government and industry and academia and people on the alignment forum, just like nonprofits, just effective altruism, like all in one room talking to each other. I thought that was amazing. So thanks, Richard. That was great.
Sure. Yeah. Thank you, Aryeh. And I'd like to note that, what we're doing with Clay is really to try to bring those disparate parties together to collaborate on like artifacts that many more people can share and understand all those different linkages and the progression and how different long-term concerns are exhibited a little bit in near-term systems and vice versa.
All right, lovely. And I think, Richard, you mentioned that our website is not up yet, but will be soon, and then I'll share it in the group whenever you have it.
Great. Yeah, you could also watch ai-safety.org for links to that new site.
Also, I'll just mention for Richard that he kept talking about Clay that has an S at the end. CLAIS.
Great, lovely. I'm sure it will become much more clear when I actually follow up with the links. Okay, so for now, thank you so much for everyone for coming on. And I think, almost one conclusion after every of the session is like, we need much more discussion. And I think you brought it in really nicely with that, Aryeh, with your presentation, even tying in the long-term and short-term. But even that is just two particular fields within the long-term and short-term, even within AI that, should be connecting more. So I think, I'm hoping that there will be much more cross-pollination. And I can't thank you all enough for joining. I thought the presentations were really, really stunning. I have rarely ever seen so many folks here asking for slides right away. So please do me a favor and send me any follow-up links so I can still participants hunger for it as soon as possible. Thank you so much, Robert, Aryeh, and Dan. Thanks, Bridget, for hopping on. Thanks to Kai for your rants. And I'm hoping that I'll see most of you again next Thursday. And we're going to publish next Thursday's topic very, very soon. And I think it should be of interest to many folks here on the call. All right. Well, with that being said, thank you for staying on for so much longer. And I hope you have a lovely day. And I'll be in touch by email.